What if your car could talk to that traffic light a mile up the road? Or what if it could warn the car behind you that you're about to slam on the brakes, even before your foot hits the pedal? Now, this isn't some far-off sci-fi dream. It's the very real future of driving. It's a world where our cars are in a constant conversation with everything around them. But to build that safer, smarter future, we've got to solve some massive technological puzzles first.
So the technology that makes all this possible is called V2X, which stands for Vehicle to Everything. It's a pretty simple concept, right? But the implications are absolutely profound. Your car gets a heads up from a traffic signal to smooth out its speed, or it instantly tells the cars around you about a sudden stop. This is really the next frontier in automotive safety, and the whole thing hinges on this seamless, real-time chatter between, well, everything. Here's the catch, though. Our traditional cellular networks, they just can't keep up. They're built on this rigid, old-school hardware, and frankly, they're too slow. And that's where O-RAN, or the Open Radio Access Network, comes into the picture. Think of it like this. You're upgrading from an old, clunky flip phone to the latest smartphone. Instead of being locked into one company's box, O-RAN is all about software. It's flexible. And most importantly, it pushes the thinking right out to the edge of the network, closer to the cars themselves. And that's absolutely crucial for things moving at highway speeds. So on paper, V2X and O-RAN seem like a perfect match, don't they? But the road from the lab to your local freeway is packed with some really serious obstacles. So today, we're going to break down the 5 biggest research challenges that scientists and engineers are literally racing to solve right now. Okay, first up, the biggest hurdle of them all, the latency wall. You know when a car needs to automatically brake to avoid a crash? Every single millisecond counts. There is absolutely positively no room for delay. And that's the bottom line. For these super critical safety applications, we're talking about an end-to-end latency. That's the total round-trip time for a signal of between 1 and 5 milliseconds. That is literally faster than you can blink. A traditional network that has to send data all the way back to some central brain and then back to the car, no way. It just can't hit that target. O-RAN's answer to this is something called the near real-time RIC. You can basically think of it as a mini-grain living right at the edge of the network, running these specialized AI apps that make decisions locally and instantly. The real challenge for researchers is creating AI models that are so ridiculously fast they can predict a car's next move and manage the network resources for it, all before the driver even thinks about turning the wheel.
Which really brings us to the fundamental question that researchers are grappling with here. It's not just about processing data fast. It's about doing it reliably, instantly, for a car that's just barreling down the highway at 70 miles an hour.
All right, our second hurdle kind of builds on that first one. I love the name for it, the handover ocean. So a handover is just what happens when your phone, or in this case, your car, moves from one cell tower's coverage zone to the next. And in a busy city, this happens constantly. Yeah, a single car might have to switch towers dozens of times in just 1 minute. Now imagine that multiplied by hundreds or even thousands of cars all stuck in rush hour traffic. The result is what engineers call a signaling storm. It's this massive tidal wave of requests that could completely overwhelm and just crash the entire network.
Now, there is a pretty clever solution being worked on called group handovers. The idea is, instead of every single car making its own request to switch towers, a whole platoon of cars is treated as one single unit. So you get one request instead of 100. The problem is, the AI needed to instantly form, manage, and then break up these groups as cars merge and exit. Well, it's incredibly complex, and it's not quite there yet.
So the multi-billion-dollar question for this challenge really comes down to stability. How in the world do you design an intelligent system that can manage this constant, chaotic motion without bringing the whole network to its knees? Okay, this next one leads us to this really fascinating clash of cultures, the interoperability paradox. See, O-RAN is built on this foundation of openness, of collaboration. The auto industry, though, historically, not so much. What you have are two totally different worlds colliding. On one side, you've got the open, collaborative spirit of modern telecom, and on the other, you have car manufacturers, each with their own proprietary software, their own unique data formats, and these fiercely guarded safety standards. For V2X to actually work, the network needs to understand the data coming from every single vehicle, no matter who made it. So the research challenge becomes, can we build a kind of universal translator right into the O-RAN system? A piece of software that can interpret and prioritize data from a Ford, a Tesla, and a giant Freightliner truck, all in milliseconds, without adding even a single drop of latency. Okay, challenge number 4, security. Look, anytime you open up a network with standard parts and pieces, you are inevitably creating more potential doors for bad actors to try and get in. And when it comes to connected cars, the stakes are unbelievably high. Researchers are really focused on two major threats here. First is something called data poisoning. This is where an attacker feeds bad information to the network's AI, basically trying to trick it into causing accidents. And the second is what's known as zero-trust mobility. In simple terms, how do you constantly make sure that a vehicle is who it says it is and not some malicious actor just pretending to be a regular car?
And that really gets to the core of the security problem. The digital handshake we use today for authentication is just way too slow for a car that might be switching networks every 30 seconds. We need a whole new security framework that can establish trust in microseconds, over and over and over again.
And that brings us to our fifth and final challenge, which I like to call the AI Hunger Games. You see, the magic of ORAN comes from its intelligence, right? But that intelligence is incredibly hungry. It needs a ton of data and processing power to work. A huge issue they're trying to solve is the domain shift problem. An AI model that was trained on data from a sunny Sunday with light traffic in Arizona might completely fall apart when it suddenly encounters the chaos of a rainy Tuesday rush hour in London. The real world is just infinitely more variable, and the AI has to be able to adapt on the fly. One of the most promising solutions here is something called federated learning. So instead of sending all this raw, sensitive data to a central cloud, the AI models are actually trained locally, on the cars themselves and on the network edge. This is great for privacy, but the challenge is kind of like trying to get thousands of individual musicians to play a symphony in perfect harmony without a conductor. How do you get all these separate AIs to work together for the good of the whole network? So, after navigating all 5 of these challenges, what becomes really clear is that ORAN truly does hold the key to a future with a seamless, efficient, and most importantly, a much safer transportation system for all of us. But as we've seen, getting there means solving some incredibly complex problems. And it's so important to remember that this isn't just about building a faster network. It's about building a system that we can literally trust with our lives. At its core, it is a safety challenge. The work is tough, no doubt, and the road ahead is long. But the destination, a world with zero traffic fatalities, makes the entire journey worth it. The real question isn't if we'll solve these technical problems, but whether we as a society are ready to place our trust in an intelligent network to get us there safely.